Okay, so I think we should start. I have the honor today to introduce the distinguished speaker, Professor Kivelson, who is actually the least known and famous and important of the Kivelsons. His mother and father are way, way more important than him, but still it was easier to get him here. Steve did his PhD at Harvard a long time ago. I'm not going to say when, so you will not guess his age. And then he was a postdoc at the ITP in Santa Barbara, working with Bob Schrieffer. Then went to Stony Brook as a faculty, moved to UCLA in order to learn more from his parents. And then when he learned enough, we managed to get him here in 2004. And he's here since, and most probably will not leave this place because nobody will hire him because he's too old now. Anyway, Steve is a leader in theoretical physics, theoretical condensed matter physics. He made many important contributions to the field. Even he was able to coin quite a few terms such as electronic liquid crystalline phases in solids, intertwined order, vestigial order, and he's still strong in coining new terms and finding new physics in condensed matter physics, particularly associated with magnetism, superconductivity, and other strongly correlated electron systems. Steve was awarded the Bardeen Prize in 2012. He is a member of the American Academy of Arts and Sciences and a member of the National Academy of Science, and he will give today, I know, a blackboard, actually whiteboard talk, which is interesting because his hand is not doing well. I had to twist his arm to get him to give this talk. So maybe he is going to use his left hand, but I hope it will be still okay. Steve.
Can you help me up? I'm sort of old and... Thanks. Okay, so we'll see how this goes. I thought to try doing a Blackboard talk. At least I figured that that would please my long-standing friend Daniel Fisher, who approves of these things. Let's see, because it's a whiteboard talk, I'm not going to be able to do justice to referencing. I've written out some of the references which I'll refer to, but on the whole, please forgive me for poor referencing. Ask me if you want to know anything about that. I guess one of the advantages of a talk like this as opposed to a transparency talk is that it hopefully will invite questions and comments. And I have about 6 hours of material. Won't get through it anyway, so you might as well interrupt me. All right, so up here is the outline, and the first topic I'm going to discuss is fundamental versus emergent gauge symmetries. So when I was learning physics, I was taught that gauge symmetries were somehow fundamental in the structure of the universe, that we could try to debate about just what's the right gauge symmetry, but we should start with the notion that we had some fundamental description which has a gauge symmetry which is exact. In In condensed matter physics, the only gauge symmetry we have that's exact is the electromagnetic gauge symmetry. And since for most purposes the electromagnetic gauge fields can be treated as non-dynamical in condensed matter physics, this is useful as a probe of properties of condensed matter systems. It's good for checking to make sure you haven't done something really stupid, but it's not what I'm talking about. The notion of an emergent gauge symmetry is the notion that in the effective low energy description of a system, the best way to understand it is in terms of a system that effectively has a gauge symmetry. So the idea is that first there's some reduction from the full Hilbert space down to some effective, okay, that's good. Some effective Hilbert space. And then we can write the Hamiltonian somehow for the remaining degrees of freedom in terms of an effective Hamiltonian which operates in this low energy sector of the Hilbert space, and then everything else. And this H effective behaves like a gauge theory. It has, at least it has a description in which there is a gauge invariance. And so the right way to understand the low energy physics is in terms of this. But unlike in the case of an exact gauge symmetry, it doesn't mean that the true universe has this gauge symmetry. There are non-gauge invariant quantities, but the non-gauge invariant quantities have no matrix elements in the low energy Hilbert space. They only have matrix elements that take you from the low energy Hilbert space to high energy states. And so they can be neglected if you're interested in the low energy physics of the system. They're irrelevant in the technical sense. So what does that mean? Well, it means that probably we will give the description in terms of some set of gauge fields. We'll see roughly what those are. We'll have terms in H effective that go like E squared, where E is some effective electric field. This will play the role, well, in my way of parsing things, as the potential energy of the system. And then there will be terms that go like B squared, and these will be things that play the role of the kinetic energy of our system. But there's other features of the theory, features that come directly from the emergent gauge symmetry. There are topological degeneracies. Roughly speaking, if we put our system, say, on a torus, we can put different amounts of flux through the holes in the torus, and in that way get to different equivalent ground states of the system. And most directly physical for the purposes that I'm interested in, we'll get fractionalization. And so fractionalization means that we're going to get quasi-particles that have quantum numbers, I'll call that charge, which are a fraction of the charges of the fundamental constituents of our system. And this is possible only if we have some sort of an exotic state of matter, and in general, for reasons that I'm going to explain, it's most natural to describe this in terms of the deconfined phase of an effective gauge theory. So there's something that is a little bit confusing when at least when I think about the problem. The idea of fractional charge, of course, there's fractionally charged quarks at some high energy, and if you're in a confined phase, the low energy excitations are all integer charged objects. This is sort of going backwards from that. Here we're imagining systems where at high energy we have all objects with integer charge, and at low energy we have excitations that behave like free particles but which have fractional charge. And these are associated with deconfined phases of our gauge theory. Okay, so that's the sort of high-level picture of what I'm going to discuss. I'm going to discuss where these emergent gauge theories come from, why they're natural as a description of certain classes of systems, how, in particular, fractionalization and deconfinement arises, and how we can combine these to get a satisfactory theoretical description of the system.
So the Hilbert basically the gauge theory plus the quasi-particles. Am I understanding?
So,
Particles emerging.
Yeah, so it depends on the case, but yes, there will be, in general, both matter fields and gauge fields. Good. So,
you just raised the question of whether the deconfinement happens in the UV or the IR. What's the resolution? How is it different than ordinary QCD? Because the RG flow seems to be backward.
So it's not different. It's just a very different perspective on what you're looking at. So, we're looking in the opposite direction that you usually do. And of course, in a confined phase, you have the smaller charge at high energy and the bigger charge at low energy. Here, we're looking at phases where you have the bigger charge at high energy and the smaller charge at low energy. Yeah?
Can you get effective Hamiltonians that are asymptotically free, or does it have to have some
I don't know what the answer to that is. Okay, so let me start easily. We'll get to gauge theories, but I'm going to first look at my second topic, which is topology and fractionalization in 1D. And here we can discuss these things without having to worry about gauge theories, and so things are much easier. And not only that, here we can deal with a problem that's physical in the sense that experiments have been done, the effects that we compute are seen very dramatically in experiments. Okay, I didn't discuss the first set of references. I'll try to get back to that, but here this is to do with body of work that came from the studying of some conducting polymers, polyacetylene, experiments that were done on them that saw that some of this fractionalization and its role, the role of topology in this, are things that you could actually measure in the lab. So in that sense, it's both simpler and more conventionally the in the rubric of condensed matter physics, where we value things that you can actually measure in the lab. So let me talk about the SSH model of polyacetylene. So the SSH model of polyacetylene is a model of a polymer in which I have electrons that live on the sites of this one-dimensional lattice. And there are hopping matrix elements that take an electron from one site to another. So there's a Hamiltonian, looks like minus sum over j, t, j, times Cj sigma, Cj plus 1 sigma. And the only thing that's a little bit interesting is that the hopping matrix elements between neighboring sites depends on, for instance, how far apart they are. So U, in this case, is a phonon coordinate. It's a lattice coordinate telling us about the distortion of this lattice. And in particular, the ground state of this system likes to dimerize. So the atoms move together in pairs. As a consequence, the hopping matrix element is either bigger or smaller by some amount. And then, of course, there's also the lattice part of the Hamiltonian, which depends on the coordinates and the momenta of the ions. Okay, so I've gotten a little bit ahead of myself here. This is the Hamiltonian. There's some modulation of the hoppings by the motion of the atoms. And indeed, if we have just this Hamiltonian, that is to say, if the chemical potential set equal to 0, this has the property that the average number of electrons on each site is going to be 1. And the system will have a ground state that looks like this, in which pairs of sites move next to each other, which I will represent graphically the way an organic chemist would, as being a sequence of long and short bonds. Now, this is a state of spontaneously broken symmetry, which is to say there actually are two ground states of this system. I've showed you one. What? Oh, yes, thank you. What?
You were making sure you were awake.
Yes. So that's interesting. There's a discrete broken symmetry. There are two degenerate ground states. So this is somehow some form of Ising model in which we can think of this as being one of the ground states and this is the other. I'm going to be using pictures like this a lot. So I just want to take a minute to explain what this picture look means. So this is a picture of a ground state wave function. It's a picture that represents one of the two possible ground state wave functions of this system. Now, the easiest way to think about this ground state is to go to a strong coupling limit. And so in the strong coupling limit, I'm going to take delta over 2 equals T. I'm going to imagine this dimerization is very big. And then you see that these weak bonds are missing. So this system just consists of an array of decoupled dimers. Yeah?
What prevents two dimers, or two things that are next to each other from, like, these two will go close to each other, but this guy will also go close to here. There's like a really big gap here.
Yeah, so this is the ground state. Actually, for this problem, there's a rigorous proof of this, that the ground state has period 2. So, you know, more generally, if I wrote down a very complicated Hamiltonian, I could arrange to have any pattern of ground state that you want. But for this model with nearest neighbor hoppings modulated by the hoppings, it's possible to prove that these are the two ground states.
I guess I'm just asking, what fixes the equilibrium position of the ion without the electrons to the places where they're at?
Right, so that's parameters in here. So this thing is opposed by terms, stiff springs between the atoms in this second term that I haven't been explicit about. Okay? So if we start with this strong coupling limit, this problem is very easy to understand because we have just decoupled dimers. The electronic ground state is a direct product state. On each pair of these, the spectrum consists of a bonding state at energy plus 2T and an anti-bonding state at energy minus 2T. And I put 2 electrons into the bonding state, and that's the state that corresponds to this picture. So I can write down a very explicit wave function for this. In any sort of physically reasonable limit, these bonds only differ by some small amount. But if I look at the evolution of the spectrum, so starting out here at delta equals, what did I say, 2T, where I have these two states at 2T and minus 2T, as we reduce delta, these states spread out into bands. The lower band is full, the upper band is empty, but there's a gap as long as delta is non-zero. So the state of my system is adiabatically connected to the strong coupling picture that this cartoon evokes. Right, so I'm going to draw lots of pictures like this, and the complicated language that goes with that is this is a state that's adiabatically connected to some sort of direct product state in which we have pairs of electrons in some low energy state on these bonds. Okay? Now, I've focused a lot on symmetry here. In this particular case, what this bond meant was very easy to understand in terms of chemistry. Just to give you another example, there's a model of strongly correlated systems that I might have looked at, which has nearest neighbor and next nearest neighbor interactions between spin halves on the same lattice. So this is sum over J of J times J dot Sj plus 1 plus J prime times Sj times Sj plus 2. This model has a miraculous solvable point where J prime is equal to a half J, and the Hamiltonian can be rewritten as a sum of non-commuting projectors. And the ground state of this Hamiltonian at this point can be written like this, where this means take the two spins on this bond and arrange them in a spin singlet, and then write down the direct product state of spin singlets on all of these bonds. And then as we vary J prime away from this value, these states adiabatically evolve, but as long as I don't change J prime by too much, everything evolves smoothly, so I can use the same picture. Right, so I'm going to be drawing these pictures. If Bob wants me to write down a Hamiltonian, I can write down a Hamiltonian, but the same picture is actually going to apply to many Hamiltonians. All right, good. So now here's the point. I can make, this is an Ising type broken symmetry. The topological defects in an Ising model are domain walls. Domain walls in one spatial dimension behave like point objects. So I could have a state, say, where I'm in this ground state to the left, but I'm in the other ground state to the right. What do I mean by, so if this is, say, the 0, these are even sites. Over here, the strong bond goes to the right from all even sites. Here it goes to the left from all even sites. There's a domain wall in between them. And so that's a topological excitation of our system that has finite energy that can propagate like a particle. Now, the interesting thing is that this object has fractional charge. And so why is that? Well, first, let me ignore electron spin so that here in my model here, when I go to the strong coupling limit, there's just one electron in this bonding state. So now I can count electrons in this strong limit. In fact, let me do it this way. Let me start with a piece of perfect system. Oh, shoot. Okay, perfection is hard to achieve. I start with my perfect system like this, so the charge, the system is neutral. Whatever the background charge is canceled the charge of the electrons. And now what I'm going to do is I'm going to remove one bond from here. So I've removed one electron and I've removed one bond, but I have a gapped system. I haven't done anything at infinity, so I've just introduced charge 1 into my system. But now I'm going to move bonds around. I'm going to move this guy to here, and I'm going to move this guy to here. And lo and behold, I now have two domain walls, one here and one here. The two domain walls are identical to each other, so they must have the same charge. The total charge is 1. Therefore, this has a charge that's 1/2 the charge of an electron. If I had spin in the system, then I would have charge 1/2 of spin up electron and charge 1/2 of spin down electron. So with spin, this object would have charge E, but that's still fractionalized because it would have spin 0. I've added no spin to the system, and there's no integer number of electrons that you can put together to have charge E and spin 0. Okay, now I did this construction in the strong coupling limit where each of these bonds was entirely localized, but allow me to do the following adiabatic experiment. I start with the system in its physical limit. I adiabatically evolve it to the strong coupling limit, do what I've done, separate these solitons by a large amount, and then evolve back to a physically reasonable value of the gap. Because I have a gap, because everything is exponentially localized, if these two solitons are far from each other, nothing changes as I go between the strong coupling limit and the physical limit. So my pictures are meaningful. We could do the same thing. This happens to be a period 2 charge density wave. If I had done a period 3 charge density wave, I would have made 3 domain walls, which would mean my particles would have charge 1/3 for spinless electrons, or charge 2/3 for spinful electrons.
Since you're invoking spin again, in the top picture that you have, it seems like that already has spin in it, in that, sorry, your perfect ground state, your 2 lines, those represent a singlet, right?
It represents 2 electrons.
2 electrons.
2 electrons in a bonding state, which is necessarily a singlet, right, by the Pauli exclusion principle.
So then when you move charge around, you pulled out 1 electron.
No, I pulled out 2 electrons. No, in that case, I've pulled out 1 electron of each spin. When I pulled out the bond, I pulled out both electrons on the bond. Yeah, now, once I've got these solitons, now if you wanted to add back an electron, you could, for instance, add back an electron here with spin up. Then I would have something that would have charge 0 and spin 1/2, which is also fractionalized. And actually, both of these have been seen in experiment in polyacetylene. Seen is a very complicated thing, and I direct you to this Reviews of Modern Physics article, in which we spent a lot of time explaining what seen means, but I think seen is a serious statement here. I should also say that the materials involved are the most horrible looking materials you might ever hope to see. But nonetheless,
Chicken fat used to be the
what?
Chicken fat used to be the technical term of Bell Labs.
Yeah, that may even be generous. Yes?
Sorry, so in the top diagram, I'm supposed to have removed 1 double bond, is that right?
I've removed 1 double bond, which was 2 electrons, and then I broke that up into 2 solitons, 2 domain walls.
So if I have the perfect state and I remove 1 double bond, shouldn't there be 3 single bonds in a row?
Yeah, so there were.
Oh, okay.
And then I started moving things around, so I had 2 in a row here and 2 in a row there. Okay? Good, we better get this straight, because this is the easy part. Now these solitons not only have fractional charge, but they are topological defects. I can move it like a point particle, but there is something non-local. If I have a soliton here, and I look very far to the right and very far to the left, I should be able to tell that there's a soliton in the middle, because if I ask, is the double bond to the right or to the left of an even numbered site, I will find that it's 1 on one side and 1 on the other. That's the topology of these defects. Now, it's not an accident. We couldn't have gotten fractionalization without topology. You would end up with all sorts of paradoxes. Somehow or other, there has to be something that, although you can get things that look like fractionally charged particles, if you look at the whole system, of course, you've got some finite number, some integer number of electrons, and therefore everything's got to be integer. Let me express that in a different way. This is sneaking up on gauge stuff. So suppose I had this soliton here, and I put it on a circle. And now let's put some flux through this circle. Inside the circle so the magnetic field doesn't touch anything. Now, there are two things that I know. So one thing is, because gauge invariance is as far as we're concerned, an exact symmetry of nature, if I take phi to phi naught, which is hc over E, there can be no detectable dependence of that. On the other hand, if I have a particle of charge E star and I carry it around a flux phi, I pick up a phase corresponding to an effective flux quantum, which is hc over E star. Now, if E star is a multiple of E, this is no problem. Phi naught star is smaller than phi naught, say half of it, but okay, twice this is still going to give me a phi naught. I have invariance under phi goes to phi plus phi naught. But if I have a fractionally charged particle, this is a very serious problem. This means that if I solve the quantum mechanics of this particle on the ring, I'm going to find that it depends on adding a flux quantum through the ring, and that's illegal. Now, the way it plays out is that the wave function for this thing can't possibly be single valued. How do I see that? Well, first, let's just look. This soliton, as I move this soliton, I go from one ground state phase to the other. So once I get this soliton back here, having taken it around, I'm going to be in a state like this. Maybe like this. I've converted this phase into the other phase. So even though I've taken my soliton once around my universe, I actually haven't come back to the same state I started in. I have to take it around, in this case, twice. And twice is just what I need in order to satisfy gauge invariance. So the topology forces me to have doubly valued wave functions. And if you don't believe me, make the smallest ring you can have that has a soliton, single soliton on it, make a 5-membered ring, and try to get this back to itself by going around, and you'll discover it has to go around twice. Okay, good. So that's 1D. So now let's try to take this idea and see whether we can find ways of generalizing this to higher dimensions, whether there are ways of getting fractionalized excitations in more than one dimension. Okay, well, firstly, we know the answer to that because it was given to us by Bob Laughlin. In the fractional quantum Hall effect, not only do we find fractionally charged quasiparticles, but they're necessary. And they can be understood directly from the Laughlin wave function and from the brilliant construction that he made for constructing quasiparticles. And not only are they fractionally charged, but they have fractional braiding statistics, which is related to this multivaluedness of the wave function. It means that if I take one quasiparticle around another, I don't get back to the same wave function. I get back to the same wave function multiplied by a statistical phase, theta star. So what did I want to say? Let's see. So fractional quantum Hall effect. We have E star equals E over M. We have theta star equals, I don't know, 2 pi over M, I think. And this was all understood without ever invoking gauge theory. Okay, so that should give you some pause. On the other hand, there is a very powerful and simple way of understanding all of this physics, and this is the one really self-serving reference I'm going to give, but it's also because this was actually only work that I was a kibitzing co-author on. This was the first really important and groundbreaking work of our late colleague Su-Cheng Zhang, which was to formulate the fractional quantum Hall effect in terms of matter fields, in this case composite bosons, but alternatively, well, one could do it with composite fermions as well, coupled to an emergent gauge field, which in this case is governed not by the sort of Hamiltonian that I've been reading down, but by a Chern-Simons theory. Nonetheless, this gives a very simple, compelling way of understanding the fractional quantum Hall effect and the nature of the quasi-particles in it. The quasi-particles in it, again, are topological defects, but in this case, they're fluxoids of the emergent gauge flux, accompanied by vortices of the composite Bose field. And I should mention that although much about the quantum Hall effect has been seen with extraordinary precision for many years, the observation of the fractional charge and fractional statistics directly in an experiment, in this case an interferometric experiment, is one of the new developments in our field, which is very exciting. It's been seen, well, by several people, but most notably by Mike Manfra and collaborators in 2 recent papers. Okay, so let me turn then to the more general consideration. So somehow or other, if we're going to have a natural discussion, explanation of these fractionalized particles, then we would like them to be associated with some sort of topological excitation. The Ising domain wall, which was so useful in one dimension, is clearly going to be useless to us in higher dimensions, because an Ising domain wall is a one-dimensional object in 2 dimensions, or a 3-dimensional object in a 2-dimensional object in 3 dimensions. There's no way it's a particle. We could imagine a vortex in an XY model in 2 dimensions, and that's almost what the Chern-Simons theory tells us is the way to think about the quasi-particles in the quantum Hall effect. But the problem is that a vortex in an XY model costs infinite energy. And so although it's a point particle, it's not a point particle that's going to be part of the spectrum. The only way it can be part of the spectrum is if somehow it's shielded, it's screened, which is what flux does to a vortex, and turns it into a fluxoid, which is then a finite energy point particle in 2 dimensions. Good. So that's what we're after. All right, so that's a nice abstract problem. It's a problem that took fire after the discovery of high TC, when Phil Anderson originally proposed that somehow spin liquids with fractionalized excitations might be the way to understand cuprate physics. He introduced the notion of RVB, which I'd like to call resonating valence bonds, which is what he meant by it, and I'll talk about that later, but has since come to be called rather vague, and I won't tell you what the third word is. You'll figure it out for yourself. I think, alas, it's unlikely that this has anything to do with high TC, but there's been an enormous intellectual undertaking that has been triggered by this, and so yeah, let's see. So here's where I would invite you to go to look at this. First place, with Shivaji Sandhi, we wrote a paper on the history of the emergence of these ideas. 50 years of quantum spin liquids, which appeared in Nature Reviews last year. But more to the point, there are now books on the topic. There's a very nice book by Subir Sachdev that was just published that has maybe a dozen chapters that are discussing the theory of this. The theory is actually in very good shape. We know how to write down exactly solvable models that have spin liquid states and fractionalized excitations. We know what the appropriate field theoretic description of them is. All of that's very nice and is very nicely described in Subir's book.
What happened in 1973?
What?
What happened in 1973?
1973 was when Phil wrote his paper on the triangular lattice antiferromagnet, which he claimed. So, yeah, so, you know, the interesting thing is that it's really two papers of Phil's that triggered this whole thing. Both papers are wrong, but they were enormously influential and creative. Let's see. Yes. So, which brings me to topic 4A, which is spin liquid candidate materials. Now, you know, this is embarrassing.
You didn't quite tell us what a spin liquid is.
I didn't, I know, and I'm running out of time. I will try to. So a spin liquid is going to be a fractionalized phase with emergent gauge symmetry, or that's well described by emergent gauge symmetries.
And no broken spin symmetry.
So that's actually secondary. I mean, yes, all of the spin liquid phases I'm going to be discussing are going to have no other broken symmetries, but there's no reason you couldn't have whatever broken symmetries you want as long as you, in addition, have fractionalized excitations and emergent gauge theories. Good. Yeah, so let me say the embarrassing thing, and then I'll go on with as much as I'm able to do in the remaining time. So the embarrassing thing is that we don't have any material that we can go to you and say, we're really certain that this hosts a quantum spin liquid. Undoubtedly, in my opinion, the best candidate is a sort of fraught term today, but at any rate, the best candidate is this Herbert Smithite and related materials that have been heroically studied by Young Lee and collaborators. But I think it's fair to say that there's no material that there's unambiguous evidence that we've actually seen a spin liquid phase in it. I went back and found that in 2010, Patrick Lee gave a colloquium here declaring victory. It was called The End of the Drought. And he had all sorts of materials that had been proven to have spin liquid ground states. I think a large fraction of those experiments have proven to be either wrong or misinterpreted. And I don't think any of the materials that he was most excited about are popular candidates at this moment. With some group of people, we wrote a review article not so long ago, in which we went through our analysis of what were the best spin liquid candidates. Many of these materials may in the end turn out to be spin liquids. It's just that in identifying the first, you would like to have a very high standard, and that hasn't been met. There is a recent development which is by the Harvard group. They've made sort of artificial materials with Rydberg atoms in some arrays and have presented moderately compelling evidence that they can achieve a spin liquid phase there. That's not exactly the experiment that a condensed matter physicist would like, but nonetheless, that's very exciting as well. All right, so with that apology, let me, and the other thing I wanted to say is the classical analog of this, classical systems, in particular certain spin ice materials, exhibit fractionalization of the sort that I'm describing, but just in a classical system, not in a quantum system. All right, so, well, let's see. In 5 minutes, what can I tell you about quantum spin liquids? Let me do the best I can. Okay, here. So the first thing I would like is to find systems that exhibit a constrained Hilbert space. There are two ideas and exactly solvable models you can write down that realize these ideas of how you might get such a constrained state. One thing is that maybe I have a system, I've drawn it on a square lattice. I'm partly because I can't draw three-dimensional systems. There's no reason you shouldn't be thinking about 3 dimensions here. Partly it's because I probably should be doing a non-bipartite lattice, but that's even harder. But so make the point on a square lattice, but don't take the square lattice too seriously. So suppose I have some chemistry that says that the electron on each of these sites likes to form a bond with one neighboring electron. This can be done with spins, as I showed you in the Majumdar-Ghosh model. There is a spin model called the Klein model that does this. Or it could be done with electron-phonon coupling, as I did in polyacetylene. At the end of the day, what I want to argue is that there are some Hamiltonians whose ground states consist of pair each site with a neighboring site, put the 2 electrons into some sort of gapped singlet state, and this is a basis state, and my low energy, which I'll label by a dimer configuration on this lattice, and then my low energy Hilbert space is going to be spanned by these dimer states. So this is a hardcore dimer constraint. Since I'm running out of time, I'm going to just assert that there are Hamiltonians that have states like this, have ground state manifolds like this. The other possibility, which goes back actually to Pauling's idea of ice, is that I could have ground states. Again, let's draw sites on the square lattice, but suppose I have another atom that lives on the bonds. And suppose this atom likes to be near a neighbor, but doesn't like to be too near other such neighbors. So, for instance, the sorts of ground states I might have is this guy moves in, and this guy moves in, and that guy moves out, and that guy moves out. This allows me to relate the ground state manifolds to configurations of some vertex model. No. In which I have, well, in this case, 2 in and 2 out, and all ways of tiling the lattice this way. Again, I will characterize the low energy space by the configurations of my vertices, and this is called a vertex model. And if z is the coordination number, then I want z over 2 in and z over 2 out. Right, why is this good? Well, this is half of what I want to get a gauge theory. This is going to play the role of Gauss's law. What you can see here, well, here directly, if you think about these as electric field lines, then every site has as many electric field lines coming in as coming out. So this is, in some generalized sense, the condition that del dot E on every vertex is 0. This is a little bit different. Here, my electric fields are not going to be vectors, they're going to be Ising variables, say tau equals 1 for a bond that's strong, and tau equals 0 for a bond that isn't strong. And this is similarly a constraint that sum over all of the bonds coming into each site of tau is equal to 1, which is to say it's something like a Gauss's law saying that del dot E is equal to 1. Okay, so that's the classical part of our theory. We now need to develop dynamics. Aaron, can I go 5 minutes?
For me, yes.
Okay. All right, I'm going to prevail upon you and go 5 more minutes, and then I really will stop. I'm now going to introduce some dynamics into this problem. Now, the dynamics that I can introduce are very constrained because my low energy dynamics need to satisfy these constraints. So I can't, for instance, have a term in which one of these strong bonds disappears, because then I violate the constraint. I go out of my low energy Hilbert space. I can't introduce a dynamical term in which this strong bond moves from here to there, because then I violate my constraint and go out of the low energy Hilbert space. If I want to introduce dynamics that, I guess I should do that over here. If I want to introduce dynamics within the low energy Hilbert space, the only sorts of things I can do is a term that, for instance, flips a pair of dimers from one direction to another. Or in the vertex model, takes a set of vertices and inverts them. Okay. And good. Trying to figure out how to reduce the remaining 2 hours and 45 minutes into 4 minutes. Let me show why this is like magnetic flux. So let's imagine that I've turned on this dynamics and I've found the ground state of my system. So the ground state is some superposition of the states in the low energy Hilbert space. And now I'm going to construct an excited state. This excited state is going to be constructed as follows. I'm going to draw a line through my system. And for the case of the dimer problem, I'm going to count the number of dimers that cross this line. That will be called n of c. And I'm going to let theta be equal to pi times n of c. So e to the I theta is 1 if an even number of dimers cross this line, and it's equal to -1 if an odd number cross this line. So this is going to make a big change in this wave function. It's going to make it orthogonal, or in the thermodynamic limit, it will make it orthogonal to the original wave function. But it's not going to affect its energy. In order to affect its energy, I have to take expectation value of the Hamiltonian in this state. Now the Hamiltonian moves around dimers, but it moves dimers around in loops. So, for instance, if I originally had 2 dimers here, and I apply this kinetic energy term that I just wrote down here, it will flip it to this configuration. But that will change the number of dimers by 2. In fact, any closed loop that cuts this line, if I resonate around that loop, it will change the number of dimers that cross this line by 0 or 2. So this state will be degenerate with this state. In the case of the vertex model, so that's the degeneracy one expects of an Ising gauge theory. If I have this vertex model, well then I can choose theta to be equal to any number times the number of lines that cross it going up minus the number that cross it going down. That will also be invariant under resonances around any loop. All right, so so that's the motivation. You can do arithmetic and map this onto a gauge theory, and I will stop at that.
So I'll start off. Of course. I'm in the front, so I can ask questions. So in the second half of the big picture, is the central idea of an enforced degeneracy of the ground state? In other words, the behavior is growing out of a special infrared of it's wackily degenerate.
Right, so it's yes and no. So it means that the system is close to a system with a wackily big degeneracy. So the construction I've used is to start with a reference Hamiltonian, which has a extensively degenerate ground state, and then perturb it. And when I perturb it, I get into this gauge theory. Now, that's not, so first place, I'm not fine-tuning. There is no massive degeneracy here. But the other thing to say is that in principle, once we're in this phase, it's a stable phase of matter, which is to say, I've gone to this extreme limit in order to be able to give you an explicit construction that gives the gauge theory. The essential low energy physics is stable until I go through a phase transition.
In the -2 minutes remaining, can you put a fractional charge into the picture for us, please?
Yeah. So, good. Let's start with, actually, let's do it for the vertex model, where the fractional charge is actually totally unquantized. So, suppose I have here a site with 2 ins and 2 outs. And somewhere over here, I also have a site with 2 ins and 2 outs. Okay? And now what I'm going to do is I want to make a pair of excitations just like we did before. And the way I'm going to do it is I'm going to find a line in which all the bonds are like this. Okay, and then I'm going to flip them. Whoops. So everywhere here, I've maintained the 2 in, 2 out constraint. Everything's happy. I've made 2 point, it costs energy, but only at 2 points. You can see that this site has 3 in and 1 out. So this is going to have some charge, Q. The charge Q is going to depend on how big the dipole moment is associated with this arrow. Okay, it's some number. It actually depends on coupling constants. So it's as fractional as you can be. It's irrational. Of course, this one necessarily has charge minus Q. And now, if I'm in a confining phase, this thing, this costs none of the energy of the constraint, but there are other terms in the Hamiltonian. This might well cost energy if we're in a, would cost energy proportional to the length if I'm in a confining phase, but if I'm in a deconfining phase, that line of flipped arrows costs nothing. And so there are my fractionalized excitations.
Steve,
That's my name.
Definition? What will satisfy you if there's a material, say, you will say, okay, a method standard of a spin liquid?
Yeah.
And also, have you told us what Hamiltonian will give us the ground state that is a spin liquid?
Yeah, so for the first time, I can tell you that. One of the problems is that we've been confused for a long time that this had something to do with strong electron-electron interactions and highly correlated electron systems. What Zhao Yu recognized some time ago is that, these sort of pictures are natural in electron phonon problems. And so we can construct electron phonon problems that are spin liquid candidate materials. Why is that exciting? Well, it's exciting for 2 reasons. One is it greatly expands the scope of spin liquid candidate materials. But there's a technical reason that this is an advantage, which is electron phonon problems can be studied by sign-free quantum Monte Carlo. And so we don't have to go to super fine-tuned extraordinary limits in order to study the problem. And so we have written down, so I'll give you an example of a model. Sorry. We is this group of people. So nearest neighbor hopping on some lattice, with some phonon coordinate that lives on the bonds, that modulates the hopping, plus k over 2 pij squared plus, 1 over 2m plus k over 2 xij squared. This model has a complicated phase diagram, but it has a spin liquid phase. If you care, it's a fully gapped Z2 spin liquid phase for some range of parameters. And that we're really confident of because we can do very reliable Monte Carlo calculations on it.
It's 2D.
So we've done it on the triangular lattice. Yes, 2D, I mean, yeah, it's sign free, but it's still hard work. And to get a stable spin liquid, we need to be on a triangular lattice. So this is on a triangular lattice, and it's for some, range of parameters.
So what would satisfy you if someone tells you they find a spin liquid?
So, it depends on the spin liquid. So the nicest thing would be a three-dimensional system with a U1 spin liquid. This would have 2 extra acoustic modes that would go to 0. Seeing 2 extra acoustic phonon modes would be a smoking gun. I don't think there's any other way of getting that. Of course, directly observing the fractional charge would be another way. There are various ways to do it. That turns out to be technically hard. One of the problems is that most of the ways people have gone about trying to establish spin liquids in experiment is by doing experiments that rule out it being anything else. And once you've done that, the only thing left standing is a spin liquid. And, okay, that's the best we have in most cases. That's not unreasonable, but that always leaves people able to say, well, what about this?
Yeah.
I have a similar question as yet. So for 2D spin liquids, let's say, what evidence would you like to see to prove we have a spin liquid? Are fractionalized excitations enough? Do you want something to see about the quantum entanglement in topological order?
No, that's too hard. Yeah, fractional excitations would be fine. Yeah, if you can establish fractionalized excitations, I think we're in business. And, there are ways of doing that. I can discuss those. They're hard, but they're not impossible in principle. Yeah, measuring entanglement entropy, I don't think is going to happen. And topological degeneracy, probably also. Well, that's actually more hopeful. You can, there are these clever ways of taking crystalline topological defects, and if you have crystalline topological defects and you have spin liquids that have topological excitations, that there are certain characteristic features that basically come from the topological degeneracy. So that's not completely hopeless.
Can you have it with screw dislocations, material with screw dislocations?
Yeah,
2D?
Yeah. That's the sort of thing people have thought about, exactly. I mean, one of the things that I would like is that if you have a two-dimensional spin liquid, it means you have a separate gauge symmetry for each plane. It means that anything that tunnels an electron from one plane to another is not gauge invariant, so it's irrelevant. Which means that if you're lucky, you should see some infinite anisotropy in, say, transport properties, that the ratio of the resistivity or the thermal conductivity or something in plane versus out of plane will vanish as the temperature goes to 0. That would show that the excitations that are carrying the current in the plane are confined in terms of their motion in the third direction. So that would be an extremely dramatic finding.
Other questions? Comments? Tomatoes at the speaker?
No, don't ask for that.
Okay, so.
What is two acoustic mode?
What?
What do you mean by two acoustic?
So you'll have a photon.